streaming started from when we saw that first click.
This is cool.
A few different pieces. Yeah, but it's fun.
This is cool. It's going to be a YouTube video then.
Yeah, so it'll be a YouTube video, and then I'll be able to edit out pieces of our little messy beginning. But
Okay.
right now we have 84 folks joining us already. We've already had 3 likes, Sujay. You're a pretty popular guy. So
I'm not that.
I don't know if I've had any likes before the video started before. So all right. Well, it's 12:30 Central Time. So we'll get started here. Thank you, everybody who is joining us live to kick off Wisconsin Salt Awareness Week 2023. So I'm Allison Madison with Wisconsin Saltwise. Saltwise is a coalition of organizations across Wisconsin. We've got municipalities, governmental agencies, nonprofits, and private partners that are working on this issue year-round. We've got dedicated partners who are hosting equipment open houses, trainings, running educational events, and local monitoring programs. So this morning, well, I guess it's afternoon, before we get started, I just want to say a special thanks to a number of our planning partners who have been working in their local watersheds years before the first Salt Awareness Week. So a big shout out to the City of Superior, Waukesha County, the Fox Wolf Watershed Alliance, Milwaukee Riverkeeper, the Root Pike Watershed Initiative Network, and the Wisconsin DNR for being a part of our planning team. So without further ado, I'm going to be handing it off to Dr. Sujay Kaushal, joining us from the University of Maryland. During Dr. Kaushal's talk, you can type any questions that you have into the chat, and then I'll be sharing those out at the end. If you have any issues with the chat, just email them to me, wisaltwise@gmail.com. And then this video will be archived on our YouTube, so you can always share it with others. So Sujay, the floor is yours.
Well, thanks a lot, Allison. It's a pleasure to be here, and I really appreciate the opportunity to participate. So let's see if I can find this again. Oops. We were testing it out, and sorry about this. Okay, hold on. Okay, let's see if this works. Okay. Can you see that?
Yep.
Okay.
All the slides on the panel, and it's like, yep, perfect.
Okay. Thank you so much, Allison. It's a pleasure to be here and talking about this issue in winter. And so Allison asked me to actually talk about freshwater salinization as an emerging global issue. And if you hear some cheers in the background or shouts, that's not for this talk. One of our PhD students just recently defended in our lab just a few minutes ago, actually. So as you all know, freshwater salinization has been gaining a lot of attention over recent decades in particular. And there are issues associated with drinking water, which I'm going to talk about today. There's also issues associated with aquatic life, where researchers have found that there are thresholds that are being surpassed for aquatic life. And what I'll talk about today also is that it's not just the salt itself that causes issues, but the salt actually mobilizes other contaminants or mixtures of contaminants that we call chemical cocktails. And so this has been a kind of a long process where, our science and recognition of this issue of the, rapidly expanding magnitude and scope of the issue has been changing over decades. But there's more and more public interest in this and more political will to try and look into ways to manage this in terms of policy. And thanks for Allison, and groups similar to Allison's that are raising awareness. So this is an issue that hit home for me personally. Several years ago, I was interviewed by the Washington Post because we live in Maryland in the DC suburbs, and the water in the area was turning blackish brown. And they asked me, they're like, Sujay, why is this happening? Can you talk about this? And basically what was happening was, in our region, we have a lot of cast iron pipes. The salt was interacting with the pipes and then leaching manganese into the water. Manganese can be a neurotoxin. There's a lot of growing interest in manganese as a contaminant, including by our water supplier, our water utility. And so there was an issue where this was happening, and I explained it to the reporter. And then a couple of hours later, our neighbor came over and said, Sujay, have you noticed that our water's been turning brownish black over the last couple of weeks? And immediately I realized that our home water was contaminated due to this issue. And I knew what to do. I called our water supplier and asked them to flush the lines in our part of the neighborhood to get this, to get the manganese flushed out of the system. But this is an issue where people aren't they're not always, we always assume that our water is of high quality coming out of the tap, but there's lots of interactions that can come after the water leaves the treatment plant. And if it's salty water, that can affect the corrosivity of the water, and then it can interact with home plumbing and the piped infrastructure before it gets to your house, leading to a different quality water, and then sometimes enriched in metals such as copper and other metals that are in solder and joints. Or manganese, like in the case of this with old cast iron pipes. So what I'm going to talk about today is that freshwater salinization, the increasing trends in ions that we see in the water, salt ions that are dissolved in the water, are causing a constellation of impacts, almost like a syndrome, like a medical analogy, where there are these different symptoms that are a collection of symptoms that are being presented in the environment that, that really represent a syndrome. And then I'll talk about the risks of freshwater salinization syndrome. What are some of the risks to infrastructure? What are some of the risks potentially in terms of human health? I'll touch on that. And then lastly, I'll talk about managing freshwater salinization syndrome. How can we treat freshwater salinization syndrome, or what's the prospect for managing this as an issue? So in terms of what is freshwater salinization syndrome, almost 20 years ago, we published a paper where it was looking at increasing chloride trends in a major drinking water supply in the eastern United States for Baltimore, Maryland. And we found that there were increasing concentrations in urban streams around our region that were linked to impervious surface cover. So parking lots and pavements, the more that the watershed experienced a hardening of the watershed and being fed a high salt diet, that affected mean levels of salinity in the streams, so that the salt concentrations were not only elevated during the winter months when road salt is applied, but they were also chronically elevated throughout the whole year, even summer and fall. And so this is a figure showing our initial trends that we reported on, where there's a quadrupling in chloride concentrations, over a couple of decades in the Baltimore drinking water supply. And we in that paper, we said that if the salinization trends continue increasing at this current rate, it could affect the potability of drinking water, major drinking water supplies over the next century. Okay. And then since that time, we've seen increasing trends in not only sodium and chloride, but other ions in water, such as potassium, magnesium, sulfate, etc. And you can see another figure from that same water supply since the 1950s showing these increasing trends of other salt ions. At that time, we didn't know what was causing all the other ions to increase, all the other salt ions. We just knew about sodium and chloride, but it turns out that all of these different ions are linked together and then changing the chemical cocktail in which what we're drinking in our home taps. So some other ions that are changing are due to development itself. The amount of parking lots, pavements, and impervious surfaces that we put down on the ground we think about building these structures or development, but we don't think about what happens when these roadways and parking lots and pavements break down. When they break down, they actually release other ions into the environment that can wash into water. For example, roadways can have calcium and carbonate in them. And so you can have increasing calcium trends. Like, for example, we looked up and down the US East Coast from Florida to New Hampshire, and we found that 2/3 of the streams and rivers were showing increases in alkalinity, which is the ability of the streams and rivers to buffer acids. And we wrote a paper. It was picked up by the media, and they called it rivers on Rolaids, because when you have an acidic acid in your stomach, you take Tums or Rolaids to neutralize it with antacids. So this was basically showing that there was a bunch of antacids that were building up in the system and that were being released in the coastal zone. Now, you may think that's great. Okay, so we're buffering all these acids, but what happens is when you increase the pH to certain levels, ammonium can become ammonia and become toxic. And you can also, we suck out water from these rivers for cooling water and recirculation water in power plants. And so you get this calcium or magnesium scale that builds up in the pipes and that can affect the infrastructure. We also have older cities in our area, in our region on the East Coast, where there's steam that's used to heat buildings. And so when you have steam, you can have calcium, magnesium contributing to scaling and affecting that infrastructure as well. So it's not all salt, even different types of salt are not always a good thing. And these are just some trends that you can see in increasing calcium concentrations. These are watersheds where there's no natural limestone in the watershed, and they were increasing. And at first we were wondering what was causing that, but then we realized it was because of all the development that had happened over years, and where people are putting down parking lots and roadways and all that. So the reason why I'm mentioning that is because we have road salt, contributing sodium and chloride. We also have the parking lots and pavements breaking down, contributing other ions. The bottom line is, the more that we develop and the more impervious surfaces that we put down, not only does that lead to more road salt that we use, but it's also very important in terms of those roadways breaking down and releasing ions and other forms of pollution into streams and rivers. So to really solve this problem, it's useful to not only limit the amount of salt that we apply, but it's also very important to limit the amount of impervious surface and development that we have. There are important conservation areas and natural areas that need to be protected, because there's environmental costs that we weren't even familiar with related to salinization, related to their development. So we now know that this is a national issue and a global issue. Allison asked me to talk about how this is a global issue, but this is a heat map on the left-hand side showing hot areas where the salinization is increasing over recent decades. You can see increasing sodium concentrations on the upper right-hand panel. This is of concern from a drinking water perspective, because these rivers and streams on these major rivers on the East Coast represent drinking water supplies that can affect people on sodium restricted diets or where people get water for dialysis centers. And then if you look on the lower right-hand side, you see an increasing trend in chloride in streams and rivers around the world. And this happens not only in places where they apply road salt, but it's happening also in Japan, believe it or not, in parts of Puerto Rico, South America. Different studies have shown this. So this is why we need to be even more aggressive and vigilant with reducing salt, because there are other sources of salt like sewage, water softeners that are also compounding and synergistically increasing salinization trends. So it's very important to limit how much salt we apply, because there's a lot of background sources. These are just examples of other ions increasing, not just sodium and chloride, from Texas to Alabama to, you see this in the Chattahoochee in Georgia. Freshwater salinization is not impacting every stream and river in the United States, but it is impacting many major streams and rivers on a continental scale. And then we decided to look at global trends, and you can see here, this is a figure. I know the fonts are small, but it's happening in Russia, Greece, Asia, parts of Asia, Europe. We have most of the data from Europe and North America, but it's happening around the world. Again, not in every stream and river around the world, but in some major rivers like the Rhine River, Even the Great Lakes, the Laurentian Great Lakes represent about 20% of the world's fresh water. And even those Great Lakes, you can see in this figure, if you squint, and you look hard enough, Lake Superior, Lake Huron, they're showing increasing trends in salinization. So even large bodies of water, even though there can be dilution, there are increasing salinization trends affecting those major water supplies in the world. So this is now a global issue, and we propose that for 20 years or so we studied freshwater salinization, and now we're studying freshwater salinization syndrome, which is the constellation or collection of different water quality impacts that are associated with freshwater salinization. And so freshwater salinization, it starts off based on the type of geology that you have in the watershed. And actually also the types of atmospheric deposition or rain that you have in the watershed can affect, how much salt that you initially get in streams. And so what happens is, based on the type of geology and the type of rainwater, and yes, some rainwater can be saltier than others. We've actually documented increasing trends in some of these salt ions in areas of the US in atmospheric deposition. And we think that could be aerosolization of road salts into the atmosphere, and then that can then fall down as rain. So you can also get other reactions in the environment as rocks break down or parking lots and pavements break down. That can contribute salts. You can have increased human inputs from not only road salt, but agricultural lime, wastewater, fracking brines, mine drainage. They all contribute salts. And then you can get biological processes, although these have been less studied. And then the end output is that in rivers, you can get drinking water contamination, mobilization of metals and nutrients, because the salts basically displace these metals and nutrients that are attached onto exchange sites. They can release them into solution, which can lead to drinking water issues. It can also affect the acidity or the acid balance in water quality in coastal zones as well. So there are far-reaching impacts of salinization that we never really imagined or dreamed of when we first started looking at this issue many years ago. So there are also, in addition to this syndrome, let's see, I'm trying to get the slide to advance. Oh yeah, here we are. There's different factors contributing to it on a global scale. And so, and this happens, regionally across the United States as well. There's climate, for example, in the Western United States, some of those water bodies are more prone to salinization because there's increased precipitation, evaporation, droughts. And as we know, not only is salinization changing, but our climate is changing as well. So, the important aspect of this is that it's not only, you may say, oh, Sujay, well, there's global warming and maybe there'll be less road salt use. Well, there's also studies that show that the extremes in climate are also changing in regions where you can have more snow fall during a concentrated period of time than in previous years. And so those are some of the patterns we've been seeing, increasing climate variability in the mid-Atlantic US. And then there's other areas of the United States that really weren't affected by snow events in the past, like Texas, for example, last year, or Oregon this year, the Puget Sound area, that are being affected by snow events. So this is not an issue that's likely going away in the near future. The climate variability might affect how much road salt is applied as well. And then finally, with warming water temperatures, and we've written papers on warming water temperatures, there can be evaporative concentration of salt. So when that water evaporates, it can actually concentrate salts. So there's also a geological aspect to it, the types of geology in the background geology. Some areas, like in the Midwestern United States, you have sedimentary lithology, and those rocks can easily dissolve, break apart, releasing ions. That's what makes the Midwest such a great agricultural area, because basically they're rich in calcium, magnesium, and lime. And but that can also contribute to the salinization issue. Human activities are also important. You get road salts, changes in land use. Fertilizers have chloride, agricultural fertilizers, agricultural lime. Household products, we use, sodium and borates. Mining, and there's just a wide variety of other, salt sources. So again, road salt is a very big contributor. we have these background anthropogenic human, these different salts coming from pollution, we need to be even more careful with the salt because it's coming from so many different places. Their flow paths are also important in terms of how we manage water. That has also contributed to salinization. And then time, these are issues that are changing over time. So we found that these main risk factors, these are the 5 main risk factors for, leading to freshwater salinization syndrome. Just like you'd go to the doctor and you would know your risk factors for heart disease or diabetes and change your lifestyle based on the knowledge of your risk factors. We can prioritize which watersheds may be most at risk from a salinization issue based on these factors. So what are the risks of freshwater salinization syndrome? Well, there can be environmental and health impacts. Freshwater salinization can affect aquatic life. It can also affect drinking water quality, which are components of our Clean Water Act. And so these are just a few pictures of salt in the environment. You've all seen this before in your own life. I'll talk about contaminant mobilization as a risk and the formation of chemical cocktails. So this is from work that we've been doing in Maryland and also other areas of the United States. And although salts aren't often regulated, they're definitely not regulated at a federal level. One of the contaminants of concern in the Chesapeake Bay watershed is nitrogen. So excess nitrogen can contribute as a fertilizer. It can contribute when it's in streams and rivers. It can go downstream and then contribute to the overgrowth of algae and bacteria. When that algae and bacteria grow, and they die, and then when they die, they can consume oxygen during the decomposition process. We found that increased salinization can mobilize nitrogen, and other studies have found this too, other studies in Europe, and it can mobilize ammonium, it can immobilize nitrate, and it can immobilize dissolved organic nitrogen. But these are results from experiments from a graduate student in our lab a couple of years ago, where they dosed with different levels of salt, and we saw increased nitrogen, being released. But it's not just nitrogen that can be released; it's also toxic metals. So in these same types of experiments, these are dose concentration curves where we added different levels of salt. And when you add different levels of salt, we saw that there were increases in manganese, zinc, strontium, and copper. And other work has shown that there's release of radionuclides that are associated with increased sodium as well. So we haven't fully discovered all the different elements that are mobilized by salts due to basically, there's a variety of different mechanisms, but basically these different contaminants will stick onto the clays and organic matter in soils, and then the positively charged sodium will knock them off into solution. The other thing is that when you add sodium to soils and mud, basically the structure of the soil and mud falls apart. When it falls apart and disperses, it can release all these contaminants that are bound to it as well. The bottom line is that when you add salt, it can mobilize these different metals, nutrients, and radionuclides into water. This is of importance because it affects our drinking water intakes. This is the Potomac River near Washington, D.C., which is a major drinking water intake. It serves about 2/3 of our population in the Washington, D.C. metro area. And you can see that specific conductance, which is a proxy for salinity, it's the electrical conductivity of water, is related to, this is over maybe 30 years of data. There are strong relationships between the concentrations of salt and different ions like magnesium, chloride, sulfate, calcium, and also organic matter. And we had a recent paper looking at the relationship between salinity and organic matter, and how that might be affected, because basically when you add salt, it's like if you eat Mexican food and you like Mexican food, you feel thirsty afterwards because it's so salty and the water from your cells rushes out to the salt through diffusion. Well, when you add salt into the environment, the cells can't keep up with, organisms can't always keep up with that salt and do what's called osmoregulation. So the water rushes out of the shells and they can burst and shrivel and then release their contents and change the organic matter quality in the water. And there are also certain organic contaminants that their solubility, how easily they dissolve in water, is affected by salt. So during the treatment process, the organic matter that you have in the drinking water can interact with chlorine during the chlorination process and then affect, harmful byproducts in drinking water. So there's a lot of stuff that we have not discovered completely yet regarding, these impacts of salts and how they affect these other elements. But you can use specific conductants as a cheap, inexpensive proxy for these different elements in the environment, which suggests that we can more accurately monitor and manage the issue with conductivity sensors, which are, if you make one at home, it's like $10-15, or they're not very expensive anymore if you buy them commercially as well. So, but what all this points to is that it's not just the salt that you introduce in the environment that's the issue, it's the chemical cocktail of other contaminants and elements that are released as a result of the salt. And so, as I mentioned, you don't have to, this figure on the left is a little complicated, but it's about different groups of elements and families. Like you may remember from, a high school chemistry class or a college chemistry class, that there are families of elements that are arranged in columns in the periodic table of elements. They're grouped based on their similar properties of valence electrons. Well, in the environment, there's different metals and organic matter and nutrients that behave similarly, and salts affect a wide range of these, altogether releasing these different chemical cocktails, which have different water quality implications. Hence the blender and these different chemical cocktails. And then these go into drinking water, so we literally drink the chemical cocktails that can be affected from the salt as well. So in a recent paper that we had, we summarized some potential, we wanted to point out the potential human health implications of salinization. So this is a broad synthesis. It was put together by one of the graduate student co-authors. It's a broad synthesis of examples of sources and impacts from common freshwater salinization syndrome ions. And you can see that if you look at this table or if you look at the paper, there's diverse health and ecotoxicology implications. Salts are important in terms of regulating blood pressure, muscle relaxation, diarrhea, sodium-restricted diets, et cetera. And one of Allison's speakers this week, I can't remember, but I almost want to say that her name is Allison too, is actually a DO and speaking about health implications, which should be very interesting. So the last thing that I'll talk about is managing freshwater salinization syndrome. So, salt, when it gets in the environment, it's very difficult to get rid of the salt, but are there any chances for managing it? So one of the things that we've been looking at is how much salt can be retained in stormwater best management practices. And we spend billions of dollars on stormwater management in the United States through different stormwater wetlands, stormwater ponds, stream restorations, et cetera. And they can not only affect the flow of water moving into urban streams, but they can also affect, we know that they can influence and reduce the amounts of nutrients and sediment transported downstream as well. The question is, can they also influence salts? Well, in one of our papers, we reviewed and synthesized the role of stormwater management features and their potential for retaining salts. And we found that there was a literature on this actually, where different types of stormwater management features like infiltration, where the water goes into, basically it's funneled into the groundwater, hyporheic and floodplain exchange through stream restoration, and then detention and retention ponds, they all have the potential for retaining salt ions depending on the site and the condition. But even though these features have the potential for retaining salts, there's also the potential for exchange reactions where other harmful chemical cocktails are kicked off of exchange sites. So the question is, are these stormwater management features sinks for these salts, or are they harmful incubators of chemical cocktails released by salts? And so when you do experiments, what you find is that on your right-hand side, the more salt that we add, like for example, sodium chloride, you can get 30 to 40% retention of sodium just in the mud and muck at the bottom of these stormwater management features. That's quite a bit of sodium retention, actually. but sounds like a great thing. But on the left-hand side, you'll see that we also see mobilization of ions in exchange. So you add more sodium, yes, it's retained, and people have also worked on chloride and found that there can be some chloride retention in these stormwater management features in the groundwater, shallow groundwater. But you also get mobilization of different ions and different metals, which can be of concern. So one implication this has, and I'm not a stormwater management engineer, but it suggests that maybe this can affect how we design stormwater management features. And we typically think of promoting biological or ecological aspects, integrating those into stormwater management feature, in addition to the hydrologic and engineering components. But there may be a room for adding a geologic component where we affect the types of sediments that we use or substrates, and the minerals that we use, like zeolites, have a higher capacity for retaining certain ions than others. For experimenting around with this to in terms of ion exchange, increasing that in the environment. So this is an example of some research actually from the graduate student that I was talking about at the beginning of this talk, who just defended their PhD thesis. But the student, Joe Galella, worked on different stormwater management features on the UMD campus. And he tested to see whether these stormwater management features could hold salt and what their potential was for mobilization of contaminants. And what he found, I know that this is an overwhelming amount of information, but if you look at it, basically these are all increasing trends. So when you add salt, whether it's sodium chloride or calcium chloride or magnesium chloride, you get this increase in all these different elements. And these are different metals and nutrients. And so it shows that across the board that there's mobilization when you add salt, and you increase the amount, you get mobilization of these different contaminants and chemical cocktails. And if you look at statistically, the different types of stormwater management features have an effect on the concentration of different metals and ions. And the different types of salts, there may be some salts that are better than others. Like there are questions about sodium chloride versus magnesium chloride versus calcium chloride. They have a different potential in terms of mobilizing contaminants. But salt concentration was statistically correlated with mobilization of all major and trace contaminants. So there's just a really large influence of these salts on contaminant mobilization. We've also been looking at, it's very hard to go out there sometimes during snow events and sample. Sometimes we have to put out automated samplers. Sometimes we just go out there in person. Last year, actually, I went out every day for months sampling a stream, sometimes bringing my small son and dog with me on a sled. And, it was a couple miles in the snow, but we were able to get really interesting data. But this is an example from this type of data on our UMD campus, where you get a decrease in pH. This was published in a recent paper. So you get an acidification response when the road salt event happens, because the sodium is kicking off hydrogen ions from the soil exchange sites. So you get acidification, just like, with acid rain, when you had precipitation events, you would get an acidification of streams, depending on if you were in the northeastern United States where you have a certain geology. You get an increase in conductivity, electrical conductivity, which you would expect because of all the salt ions. You get increases in ions and metals, which I've told you about already, due to ion exchange. But then you also get changes in the quality of the organic matter. That's related to the salt. That's, we're finding out about and learning new things every day, that, the organic matter changes in its quality based on the salt content as well. But the bottom line is, salinization can lead to acidification, metals mobilization, nutrient mobilization, and reactive organics. Is not just the salt itself, but all of these indirect impacts it has. So what can we do about this? This is also some promising information from long-term monitoring at some of our sites. I'm only showing you a few years here, but we have years in Maryland where, because of the climate, we have very little salt that's applied. Like, it hasn't snowed in Maryland yet, okay? And when we look at these years, this one is in gold. It was in 2020 when the pandemic started. There was very little salt added because there was no snow that year. And then there was also not many people on campus because of the pandemic. So the need for salting campus was also reduced. When you had that kind of situation where there was less snow and there were less people on campus, there was a decrease in concentration of salt by 100-fold, depending, on the amount of roads. So it depends on the amount of road salt that's used. And I want to point out that we recently met with our University of Maryland campus, the people that work on campus, that manage salt. And there's also the parking behaviors of people, like how they park, where they park, that can affect how much salt is used. So there's a human behavior component of this whole equation that we haven't really addressed. We're not social scientists, but that can be very instrumental in, helping curb this problem and manage this problem. Okay, so lastly, because we've treated this as a syndrome, scientifically, we've mentioned all the different impacts that are associated with the ions. There's also stages of severity in terms of its effects from a contaminant mobilization perspective, as well. So stage 0, it's like where, it's minimally disturbed water. Stage 1 is where you get an increase in sodium. Stage 2 is where you get chronically elevated conditions. Stage 3 is where you start to get formation of these harmful chemical cocktails, which can start exceeding water quality thresholds. And stage 4 is actually where you start exceeding these thresholds. In where we live in the mid-Atlantic, we actually are in stage 3 and stage 4. There are certain times of year where certain thresholds for drinking water quality and aquatic life are exceeded a certain percentage of the time. And so we were able to diagnose this with sensor data. And so, but the bottom line is if you look at the risk factors on your left-hand side, we can control this issue or through knowledge and through managing flow paths like stormwater management, human activities, how much salt we apply, even how we park our cars or where we park our cars, what our expectations for cleaning roads are. And we can see these changes over time, as the example that I showed you on campus on that stream where we reduced salt and then saw a response. The management implications are it's increasing from local to global scales. It poses risks to drinking water and infrastructure. Stormwater management can retain salt ions, but mobilize contaminants. And then reducing sodium chloride inputs can lead to rapid and year-long recovery in water quality. And with that, I'd like to thank there's many collaborators and students that were involved in this, and the management community. We learn from our management community all the time. They're faced with these complex, issues. And we wanted to thank our funders. And I also wanted to thank Allison. I have never met anybody so dedicated to this issue than Allison. So, thank you for inviting us.
Well, thank you, Sujay. I mean, you're the one out there with your little son and the dog going out every day. And yeah, so thank you for joining. Thank you for a very I want to say a deep dive. I think you really opened some people's eyes to the amount of data that's out there. And I want to acknowledge a lot of the people on the call today may just be citizens. If this was overwhelming to you, it's okay. I think the big idea that Sujay shared is it is happening around the world. Not just in our northern states, but in our northern states where we're adding so much road salt. We just see it, tenfold, right? I want to share with you, Sujay, later, the animation I've made to try to make this a little more accessible to the average person. So we can do that offline, but we do have some questions here that I want to ask of you before you have to head out. And I do want to acknowledge if anybody who's joining in needs to leave now. I know we're a little after 1 o'clock, so type those questions in so I can ask them, and then you can go back and see the answer in the recording. So let's see here. We have a question about the cleanest water in the world. What are they doing to keep it clean? So I don't know if you want to talk a little bit about maybe an area where it's cleaner water than you would expect, or if there are some management practices that you've seen the benefits of as you are doing monitoring.
That's a really wonderful question. the cleanest water in the world. New York City used to brag that it had the cleanest water in the world because of the Catskills, but then there was development in the Catskills and cryptosporidium. So, this is a really excellent question. Some of the cleanest water in the United States and probably around the world also is where they had the foresight to not develop in those drinking water source waters, right? And so the only types of pollution that you get are from atmospheric deposition where there's still pollution coming in. So those are the cleanest water supplies where there's no development and it's just atmospheric inputs coming in. But that being said, in Massachusetts, Boston, for example, in Western Massachusetts, they have the Quabbin Reservoir system where they have conservation areas. So I can't stress the importance of conservation enough. We focus on restoration and stormwater management, but preserving our natural landscapes and their filtration capacity and the fact that they absorb these pollutants have the potential without adding more pollution is just so important to drinking water quality. That being said, there are drinking water supplies where there's low residential land use around the drinking water supply. But I've been meeting with drinking water suppliers about this, but there's no formal buffer zones or protections around the reservoirs, like no salt zones or things like that, where they know that location matters, that proximity matters, but they haven't specified policies spatially close to the water body. I think that could be an improvement, even if water supplies don't have that protected conservation area around them.
Mm-hmm. Well, thank you, Sujay. Yeah, and for listeners joining in Wisconsin, I know most of us are drinking groundwater, right? So we aren't necessarily thinking about a reservoir and a productive buffer around it, but it's literally, whatever is coming down on the ground above us or above those wells, is making its way into our drinking water. I think Sujay did an excellent job of, explaining that in terms of road salt, the sodium concentration. We are going to hear a bit more on Wednesday from, her name is Allison, Dr. Allison Couture, talking about the impacts of sodium concentrations, elevated sodium in our water. So Shannon Hayden had asked if we can get links to the studies that you referenced. There were many, but maybe, we can communicate. I can either grab them off your website and then put them in our salt awareness page as kind of some extra links under your bio. I think that could work, Sujay.
Yeah, I can
communicate about that. Yeah,
we can communicate with Allison. Thanks. Yeah.
All right. Blake Olson has asked, is there a way to provide a buffer to storm drains similar to buffering along streams near agricultural fields? So I think you kind of discussed that a little bit. I don't know if you want to,
Sure. Yeah. One thing I see happening around here is that where they have the curb and the storm drain, and you could have this, where a tile drain is as well, is they actually put a bag these days, in our watersheds, a bag of, I don't know if it's sawdust. And what it does is the water passes through there, and I think it's to mainly remove nutrients, but there's the potential, like I said, by adding minerals to retain salts as well. Now, when the exchange sites on the soil or the mineral gets used up and it's less effective, you probably take the bag away or leach it somewhere. I don't know. But yes, there are little barrier, like bio barriers or things like that people are putting up in the Chesapeake Bay watershed where the storm drains happen, and it's becoming more common. I think where you have the storm drain or the tile drain stream interface, that's an important area to put wetlands in or conservation and restoration measures, because that's disrupting the flow path directly from the drain to the water body.
Mm-hmm. Yeah, I think one of the biggest misconceptions when I'm talking to property owners is that rain gardens are taking care of the salt issue, right? Mm-hmm. But we know that those, especially sodium, right? The sodium can get, bound to the soil, but the chloride is going to make its way through. That those, retention ponds don't do a good job of, catching the negatively charged ions like chloride.
Yeah, they can get overwhelmed with their exchange sites. Yeah.
Okay, so we have another question here. Lance is asking what levels of sodium chloride concentrations represent the third and fourth levels of degradation that you show. So I think in that kind of step diagram. So Lance says that in his watershed, they've seen that chloride concentrations have been from 60 all the way up to 1,300 milligrams per liter. So I guess he's wondering how far are they down that freshwater salinization syndrome kind of chart.
Yeah, so Lance, we see concentrations that are 1,300 milligrams per liter. Sometimes we see them at 5,000, believe it or not, 10,000 milligrams per liter in the urban environment. But 1,300 is a good healthy dose. I will say that when we diagnosed it, we use conductivity data because there's a sensor that you can track it all throughout the snow event and get the pulse. So in terms of conductivity, the EPA, Susan Cormier's group, I think, at the EPA have set a conductivity threshold for where they start to see impairments in aquatic life for the central Appalachian region, which is close to us in Maryland. And that was around, I think, 200 microsiemens per centimeter or something like that, 225. It was a low level, actually, surprisingly. But that was based on a lot of experiments and literature work. Then, so that was one of the criteria that we used for diagnosing stage 3 and stage 4. The other was the conductivity standard for the Murray River Darling Basin in Australia, which Australia is saltier because it's got a dry climate, but above 800 microsiemens, that's their classification for good drinking water. And so we often, exceed that as in our region. And the percentage of time, I'd have to look back at the paper, like which percent, because it was like a certain percentage of time in stage 4 versus stage 3. The last threshold that we used for crop was from the USDA and for crop growth. And I think that was about 2,000 microsiemens per centimeter, where you start damaging plants at around that level. So those were the thresholds that we used to diagnose stage 3 and stage 4, and then used high frequency sensor data.
All right. Well, thank you. We've got a question from Laura. Would it be possible to share your degradation level graph? So I think, yeah. Okay.
Yeah, of course. You know what I can do is I can give Allison a copy of this slideshow, right?
Mm-hmm.
And any papers, we're happy that there's even interest, we've got
a lot of interest.
I'll send Allison like the whole enchilada and you can see what bite you want to take off of it.
All right. Sounds great. Yeah. And I would say if there are any additional questions, people can either route them to me, wisaltwise@gmail.com. I think Sujay had shared his email in that thank you acknowledgement slide. So I'll just stick on here for a moment more. I know there's a little bit of a delay. So another question or two comes in, but several people have said, thank you very much. Thoroughly enjoyed and appreciated this. Even though it's pretty new to Frankie, he looks forward to the rest of the week. So I think, this was a great kickoff, Sujay. I think acknowledging you did during your presentation, there's a lot of data on those slides. So thank you. Thank your students, including a special congrats to the one who just passed and will be graduating, hopefully. Soon. So and I just want to take a moment as I keep an eye on the questions to say thanks again for people joining in. We will continue to have webinars every day at noon 30 Central Time. So you can pass along the links to today's talk, to future talks. And thanks for your interest in this topic. So, all right, I think Sujay, we're good.
Okay.
Do you mind if I share with you right now?
Yeah, go for it. I'm very curious how you.
Okay.
It is complex.
So anybody who wants to can pop off, or you can get a little bit of a intro into what I talk about here.
Oh, you have it for chemical cocktail. Okay.
Yeah.
That's so cool.
Yeah, so I actually don't get to take full credit for this. My colleague at the Sewerage District had initially made this animation to explain how water softeners work. but it's the same
Okay.
idea, right? Ion exchange. And I have a background in soils, so I get to nerd out. I actually shared this at Nerd Night at a local bar in Madison last week. So yeah, talk to people about the idea that clay particles are negatively charged, right? They've got this ion exchange potential, so they love to hold on to positively charged things. And then when we add
Oh, that's so cool.
and the snow melts, right? We've got
Yeah.
sodium and chloride moving with snow melts through the soils. And again, those clay particles love positively charged things. So they grab a hold of the sodium. And as they do that, the other positively charged particles, and I was called out that last week at Nerd Night, I used the term ions, and that was too much for people. So I'm going to try to move to like particles.
Yeah.
That they're released. And so now we have that manganese that ended up in your drinking water, right? Potassium. So we're losing sometimes maybe some of the nutrients that the plants who drink from that soil solution need, right? The chloride is negative and the clay particles are negative. So those are not binding to one another. The chloride moves through readily through the soil, but we're left with the sodium now in our clay, in the soil. And as you mentioned, I generally don't get into that idea that it causes more like kind of soil dispersion, right? And kind of the breakdown of the soil structure. But we do have soils now that are holding on to a lot of sodium, which isn't necessarily the healthiest for those plants. So that's my little mock-up. I see some nods. So is it Sujay approved?
It's Sujay approved and Sujay critically acclaimed.
Oh, wow. All right.
Yeah, it's cool. Yeah, that's great. I mean, and do people understand it then? And then
Yeah,
yeah.
I think so. I usually before I do that, I mean, I do have one slide where I show water molecules and salt kind of dissolved in those. So we try to go over this idea of salt, breaking into sodium and chloride particles, right, in the water, and then kind of go into that. So they do get like a little preview before I throw all this at them.
That's cool. Hey, Allison, do you remember Paul Meyer from the
Yeah.
So this is my friend and longtime collaborator, Paul Meyer.
Hey, Paul.
This
Just happen to be in town.
We're live streaming.
All right.
We're on like YouTube.
Oh my God.
You're on YouTube, Paul.
Right.
You might get cut out at the end though, we do the final version. But yeah, thanks for saying hey. Were you in town for the defense?
Yes.
Okay.
Yep. Plus other things. I'm going to do field work. They're going to put me to work here.
All right.
On bike, on foot, on car.
Yeah, they're such slave drivers.
Whew. On sled. It
Yeah.
has to snow though.
I told her about Akash on the sled for Rock Creek. But Allison was like, Sujay, there's a lot of data over there. It's like overwhelming. So now I'm wondering if like we're overwhelming. But the thing is, honestly, because people weren't taking it. It's not they weren't taking it seriously, but we had to produce that data, right, Allison?
Yeah, no, you have to produce the data. You need to talk to people at this level, right, about that. But when I'm in a couple hours talking to the county highway commissioners, they aren't gonna take that. I need to provide a different kind of version of this. So
is it working? Like because I've seen your stuff is like really picked up. I see on like social media and just it's like really, and we don't have to have, I don't know who's on this call, but
yeah,
do you feel like it's like in Wisconsin?
I think so.
Yeah.
I feel like we've gotten more kind of traction just in the last couple of years since the first Salt Awareness Week. We've got the DNR has been a part of our planning team this year for the first time. We're getting, buy-in from, the DOT as talks to me. So I was able to present at the DOT their tech talk this fall, talk to staff from across the state. Like I said, I'm talking to county highway commissioners from across the state who are actually the ones in Wisconsin. The county highways maintain all state highways.
Yeah.
So we're talking about, this is decision makers for big amounts of salt that go down. So I think it's working. We're just trying to build that base, right, of people who understand and are voicing that they care about this issue. And Yeah, I think it's working, but I need your science to, is backing that up, right? Your work, the work of Bill Hintz, Hillary Dugan in Wisconsin. So,
Yeah,
Paul Meyer.
yeah. Well, no, that's awesome to hear. And I mean, you are super dedicated. I mean, I don't know. I mean, there's the Freshwater Society and the Minnesota. They're also, but I mean, you really are vigilant on this one. So, I mean, it's cool. You're very focused on it. So I like following the impacts and stuff that you're having.
Well, thank you. Well, I will let you guys go
Okay.
enjoy your lunch and celebrate with the team. So take care and tune in. I'm signing off here, everybody.
Okay. See you, Allison.
Yeah,
Bye,
Allison.
everybody.